This is part 2 of the lecture for Module 6. Now in here we're going to talk about the normal probability distribution and the standard normal distribution. I listed the different sections that I cover in these few slides. Alright, the normal probability distribution is characterized obviously by the area under the curve being 1. Otherwise it will not be a probability distribution. Another very important characteristic of the normal distribution is that it's bell-shaped and perfectly symmetric about the mean. Another characteristic is that the two tails, the tail on the left and the tail on the right, the left tail extends to minus infinity and the tail on the right extends to plus infinity. So that means that the probability for very large values of x are given by this curve, and values for very small values of x are given by this curve. And another very important characteristic of the normal distribution is that it is fully determined by the mean and the standard deviation parameters. So that perhaps you remember mu from module 3, which is the measure of central location, and sigma is the standard deviation of the population, and that's a measure of variability of the data in the distribution. Now, when I said symmetric about the mean, that means that if I were to be able to cut out this blue curve and then mark it on this black line where the mean is and fold the two sides, you will see that they will match perfectly. That's what we mean by symmetry. Right. So as you would imagine, the mean determines where the center of the distribution is located. So in this figure, I'm showing you two standard deviations with the same variability. This one is the standard deviation of 10, and this one is with the standard deviation of 10, except that the first curve, the one with the solid line, is centered at a mean of 35, and the one with the dotted line is centered at a mean of 50. Now in this other case, I'm comparing two distributions, both center at a mean of 35, but with different standard deviations. The distribution with the solid line has a mean of 5, a standard deviation of 5, and the blue line has a standard deviation of 20. So this blue, the blue dotted line, its variability is 4 times bigger of the distribution with the solid black line. So the more variable the distribution, the wider it becomes, the less variable, the narrower it becomes, and the taller it becomes. And the more variable, the wider and the shorter it becomes. And the reason that one gets bigger and the other one gets wider is because the total area under the curve must be 1. So if the distribution is very narrow because the variability is very small, so that thing is like squeezing it up. And so the total area under the curve is 1. And then if you increase the variability, so that now you're stretching that distribution, and that the top of it starts to go down because we have to maintain the area under the curve equal to 1. But now you see what is the effect of the mean parameter. It just tells where the center of the distribution is located. The standard deviation tells us how spread the distribution is, so how variable the data in that distribution is. All right. Now, if you notice, we say the normal distribution, really we're referring to a family of normal distributions, because for every pair of a mean and a standard deviation, there is a normal probability distribution. So there is an infinite number of normal probability distributions, one for each pair of mu and sigma. However, any normal distribution can be transformed into what is called the standard normal probability distribution by calculating what is called the z-score. The z-score, all it is we take each value of the original normal distribution, we subtract its mean. By doing that, we are shifting the distribution to be centered on 0. And then all those differences of the mean minus the value minus the mean, we divide by the standard deviation. That means we're standardizing those differences so that the standard deviation of this new standardized normal probability distribution is 1. So this new random variable z, whose values are the z-scores, is called the standard normal distribution, and you know that standard normal distribution, because there is only one, has a mean of 0 and a standard deviation of 1. So in this diagram, I'm showing what I explained before, that you can take any normal distribution and you can transform it by calculating the z-scores for that distribution into that standard normal probability distribution that has a mean of 0 and a standard deviation of 1. So the standard normal distribution is just another normal distribution, but this is the one that we can achieve by standardizing any normal distribution by using the z-scores. All right, the characteristics of the standard normal probability distribution are very similar to that of any member of the family of normal distributions. That means the total area under the curve is 1. The curve is symmetric about the mean. The two tails of the curve extend indefinitely. That means that this will cover values of z-scores all the way to minus infinity on the left, or z-score all the way to plus infinity on the right. And there is only one standard normal distribution with a mean of 0 and a standard deviation of 1. Now, if you notice, when I show the standard deviation here, I show this line going from the mean to this point on the curve. This is called the first point of inflection. That's where the slope of the curve changes. So the distance from the mean to the first point of inflection, that is the distance. That distance corresponds to 1 standard deviation. And that's why over here, and for the standard normal, I'm showing that distance from the mean to the first point of inflection is just 1 unit. All right, so these are you see the characteristics of the normal distribution and the standard normal distribution are very similar. Now in here, I'm showing the equivalence of the two scales. So in here, I'm showing the normal distribution with a mean of 100 and a standard deviation of 10. And what I've done, I have divided the scale for the random variable x into the mean plus 1 standard deviation plus 2 standard deviations plus 3 standard deviations. For example, this is 130 because the mean is 100 plus 3 times the standard deviation of 10. Well, that's 130. So, and then the same thing on the left side. So here 90 is the mean minus 1 standard deviation of 10. So 100 minus 10 is 90. And then minus 2 standard deviations is 80. Minus 3 standard deviation is 70. So now if you take the x values and you use the z-score formula, you can change them into z-scores. For example, you take 130. Here, x is 130 minus the mean, which is 100. So 130 minus 100 is 30. And you divide it by the standard deviation of 10, that gives you 3. So the z-score is 3 for that value. You can do the same calculation and you will find that for 120, the equivalent z-value using this mean and this standard deviation is 2. For 110, the equivalent value in the z-scale is 1. And the mean, and you can see the mean, if you take 100 minus 100 is 0, divided by 10, well, is 0. And that's why the mean of the z-scale is 0. Now, if you take the mean minus 1 standard deviation and divide it by the standard deviation, then you see that gives you minus 1. So this is minus 2 standard deviations below the mean and minus 3 standard deviations below the mean. Now, if you want to move back from z-score to x values, then you will use this formula. So you will take the mean of the original distribution plus z times the standard deviation, and that will give you the x values. But you can see how these two scales are equivalent. This is in the original x values, and this is in the z-scores. Another thing that you see is that the z-scale is in multiples of standard deviations. That means 1 standard deviation, 2 standard deviations, 3 standard deviations above the mean because they are positive, or -1 standard deviation, -2 standard deviation, -3 standard deviations because they are below the mean and the mean is 0. So you see the equivalence between the two scales. So you remember from module 3, we talked about the empirical rule. Well, the empirical rule comes from that normal distribution. And there you recall that we said that the proportion of values between the mean -1 standard deviation and the mean +1 standard deviation, it was about 68%. Well, specifically, we were saying that the probability that the random variable assumes values between the mean and -1 standard deviation and the mean and 1 standard deviation is 0.6826 or 68.3%. Remember that the probability the random variable takes values between the mean -2 standard deviations and the mean +2 standard deviations is 0.944 or 9.4%. There we simply say 95%. And the probability the random variable is between the mean -3 standard deviations and the mean +3 standard deviations is 0.9973 or 99.7. So you see the empirical rule is directly derived from the normal distribution. And the reason I'm showing these segments is using the symmetry of the normal distribution. So we know that between the mean and 1 standard deviation and the mean and 1 standard deviation, rather the probability between the mean and -1 standard deviation and the mean +1 standard deviation is 68.26%. You can divide that in two equal halves because it is symmetric about the mean, and you can divide that into 2. That's why we get 3.41 and 0.341 here. And you can go back to module 3. I explained these other numbers there. All right, so now here's the empirical rule in terms of the z-scale. So now we just simply write the probability the z random variable is between -1 and 1 is 0.6826 because we know that the z-scale is in multiples of standard deviations. So the probability that the z random variable is between -2 and 2 is 0.944. Or the probability that z is between -3 standard deviations and +3 standard deviations above and below the mean, well, is 0.9973. So now you can see that the probability remains the same. So in fact, the probability for an x value is the same for the equivalent z value. So for example, here, the probability that the random variable x is between the mean and -1 standard deviation and the mean +1 standard deviation is the exact same probability that the z random variable is between -1 and 1. And here I'm showing you the case for 2 standard deviations. So even and you see this, the scale, this is the x scale and this is the z scale. The curve and its areas under the curve do not change regardless of which scale you use. So as long as you're using the equivalent z values for the x values, the probabilities will be the same. And we're going to take advantage of this in the next section because we're going to use probabilities from a standard normal distribution to calculate probabilities for any other probability distribution. And so that means we're going to be going between z and x or between x and z. All right, finally, I wanted to point out that it's very important to remember that if the probability between the mean -3 standard deviations and the mean +3 standard deviation is 0.9973, the probability outside that range is very small. And I'm giving it right here, 0.00135, that you find that the random variable is below the mean -3 standard deviations, or that is 0.0135 that the random variable is above 3 standard deviations, the probability that is. All right, in the next section, we'll talk about finding probabilities from a normal distribution.